Okay, welcome back to part 2 of Applied Materials and Corrosion. So I was thinking maybe we'd do today something about what happens when we put our funny surface now into water. So imagining it's a metal, because we have to think about corrosion, let us put a lead on it over here. And we want to use that to be able to measure something. Okay, so if we take an atom that's in the surface, let's have this one because it's more clearly in the surface, it could dissolve out, but this one on the corner is obviously more reactive and can dissolve out more easily. If we have something in solution, it will also, so let's have a molecule in solution maybe, ooh, that's a funny molecule. Let's have a molecule in solution, it can maybe stick onto this surface, and it will stick onto the surface in different ways depending on how the atoms are organized. And this one here, this atom on the corner, is also going to be slightly more effective at attaching to our molecule, but it might have, on our molecule we might have an oxygen here and another one on here, so we might have multiple places that can attach to our surface, and it will depend what the shape of the hole is, where it will sit. It might even sit in this corner because it can then interact with multiple atoms in our surface. To start with, let's view it more simply. So let's just have a potential that a blue atom can come from the solution, so this is all solution, and attach to our surface, and it's the same as our black atom, so it's a metal, whatever it is, copper. So we can end up with a new one attaching, or we could unzip one that is already in there, so this black one could leave and go into solution. And we can see that reasonably logically, the ones at the corners, on the outside corners, are more likely to dissolve because they can go in all directions and they are not attached to as many atoms. And the ones in the inside corners are relatively unlikely to dissolve, but they're the ones that a new one will tend to attach to. So it will tend to attach here because it's attached to more sites than starting a new center, just like we had in the gas phase. So if we take a normal piece of copper and we put it into water, this process will happen, and our solution will fill up with copper 2+. So if we start off with just tap water, our solution will get a concentration of copper 2+, and as you know from the Nernst equation, the potential that we would expect to stop the copper dissolving is actually infinity, because there's a zero in there. We've got a divide by zero problem. But as soon as any copper is in solution, then we have a measurable amount of copper, and then we can use the Nernst equation. Before that, it's kind of weird because it doesn't really work. What will happen in reality? Well, we can't go down towards zero because we end up with single atoms, single ions, so something will go wrong down at extremely low concentrations. It can't work. So if we allow some copper to dissolve, that will make our electrode get negative. Whoops, let me put the negatives the way around for you. Sorry, it's the way around for me. Let me put the negatives the way around for you. So this is going to get negatively charged. And when it becomes negatively charged, the Nernst equation will start to react. So we will end up with the voltage of the electrode going towards the potential where copper can't dissolve, and the concentration of copper in our solution will go up, and eventually there will be enough copper in solution and enough negative charge that it will stop dissolving and it will go to an equilibrium. Remembering that an equilibrium is a dynamic process, so if we've reached equilibrium now, sorry, stuttering. If we've reached equilibrium now, there's copper leaving and copper joining, and now some things can happen. So our steps can start to heal, and any copper that's forming out of solution will tend to go on here, and any copper that's being lost will tend to be lost from the corners, and we will tend to end up with slightly less steps, a slightly nicer surface than we had to start with. If we wait for infinity time, we can imagine thermodynamically that we possibly would end up with a single crystal, but we would have to wait for infinity time. This is a very, very slow process because they're going mostly randomly and there isn't a lot of energy difference between them. So if we have one electrode, we will end up with a charge on it, and we could measure that if we try to measure this voltage here. But we have a problem because the solution is also charged. The solution has got copper 2+ ions in it, and it has lost effectively electrons. The solution is also positively charged, and it's positively charged compared to our electrode. So what do we measure as a standard? So if we would like to measure the voltage at our copper electrode to see how strongly the copper dissolves into the solution, we would be able to measure the voltage against something, but we'd have to have an independent measure of the voltage of the solution, and this is how we do it. In effect, we're building a battery. This is the paper, at least. It's not the physically simplest, but it's on paper the simplest because we're using a piece of platinum and the hydrogen H+ couple. So we need, let's put a frit on here, and we want to have a standard hydrogen electrode, so this needs to be 1 molar acid. Let's have HCl. And we need to bubble hydrogen through. The hydrogen needs to come in contact with our electrode, and we obviously need a hole, otherwise it would fill up with hydrogen, push all of the hydrogen chloride out. Then we've got an independent measure of the voltage of our solution, and we can measure the voltage of this electrode compared to the solution. By definition, this has a voltage of 0, so we don't have to worry about the voltage of this half cell. So effectively, we're making a cell, we're making a battery or a single cell, and measuring its voltage. Now we come to the interesting part. We can get two things out of a cell. We can get voltage and we can get current. So we can get voltage and we can get current, and we could measure both or either. The voltage is measuring one thing, so the voltage is a measure of how strongly the copper is dissolving. The stronger the copper dissolves, the more negative this voltage. The more positive this voltage, the more the copper from solution is trying to get back onto our copper electrode. So we can measure that. We have a 0. It's not an absolute 0. All electrochemical measurements are relative, but we have at least somewhere that we can compare it to. And we're effectively measuring the solution. We do have a technical problem. The technical problem is here. If we wait, obviously, for a long time, the hydrochloric acid will leak out, and whatever is in here, which was tap water, I think I said, will go inside. That will change this concentration, so it will change this voltage, and it will change the concentration of hydrogen ions in here, which will cause our copper to dissolve probably faster. So we have a lot of things that can go wrong, but at least initially we have a constant voltage. Unfortunately, as usual, we've got a problem between kinetics and thermodynamics, because theoretically here we're measuring a thermodynamic process. We're measuring how much energy do we get if copper dissolves into solution or goes onto the copper, so it comes out of solution. If we have a effectively 0 voltage compared to something that we don't know what is yet, but if we have 0 voltage compared to open circuit, then nothing would happen. So then we're at equilibrium, we do nothing. If we have a voltage that's more negative than the open circuit, where it would go on its own, then we're forcing the copper to deposit. And if we have it more positive than open circuit, we're forcing the copper to dissolve, where thermodynamically it wouldn't normally. We're using voltage to change things. The problem is obviously that thermodynamics, by definition, means that theoretically we should wait forever, and we can't wait forever with this system because of the aforementioned problem. Our hydrochloric acid will diffuse out no matter how small we make the pores. And we can't make them too small, we can't make this distance too big, and we can't make the pores too small because then we will generate resistance. And practically, we have to draw some current to measure voltage, and the more resistance that we have, the more wrong our voltage measurement will be. There's also a real shift at every membrane. There's a very real voltage because there will be a slight voltage difference between these two solutions. They're not the same solution. And the membrane or pores or whatever we have in here will be able to support a very slight voltage difference. Let us think a little bit more about what happens if we try to change the current. So if we change the voltage so that we're not at open circuit, so that something is happening, then we can have current flow. If it's open circuit, if there's nothing in here or an infinite resistance in here, no current can flow, and so we will have a voltage, but we will not be able to measure it, and we will have no current. If we allow some current to flow, we can have a voltage difference. We can change our voltage difference. We can draw some current. If we have it so that the copper is dissolving into a solution, it's not the normal way, but let's have it so that the copper is dissolving into solution, so this is now going to be negative compared to this one. We have copper dissolving into solution, and we allow current to flow, so we could close it completely with a link. Then we can't measure the voltage, so we force the voltage to the voltage of our other cell just by connecting them with a wire. The question then is, what happens? Obviously the voltage is now the same on both, and we have a high current that will flow. And what is the current dependent upon? Well, the current is dependent upon the area of this electrode, which we can imagine that would be an easy way to make more current. If we want more current in a normal battery situation, you just add more batteries in parallel. If we need more current to our radio-controlled car, we add more batteries in parallel. If we need more voltage, we add more batteries in series. If we need more current, we add more batteries in parallel. And so we can have just a bigger electrode. We could also change the temperature, but what is actually controlling it is the speed that these can leave. If we think about it locally, when the copper leaves, it's still here hanging around close to the electrode, so the local concentration of copper close to the electrode is higher than the concentration over here far away from the electrode. And it can't just jump over here magically, it has to diffuse over time. Unless we're stirring it, it has to diffuse away. And so we have a kinetic process, and so we can think of the current as telling us something about the kinetics. Depending on what we do with our geometry, it might tell us different things about the kinetics, but the current is telling us about the kinetics, how fast does the copper dissolve, and the voltage is telling us something about the thermodynamics, how strongly does the copper want to dissolve, giving it a personality which we shouldn't do. Just reminding you that that's a bad thing to do, but I do it anyway. I'm sorry about that. So we've got copper dissolving in this particular case, and we can see two extremes. Let us look at it a little bit further. The good thing about copper is it doesn't have a copper oxide layer if we control the solution properly, which is why I haven't defined it very well deliberately, so that we can imagine this copper to be bare metal. In most cases, it's not bare metal, it's got something on it. So if we do a simple experiment and we take some copper, we put it into copper sulfate solution, so that we've got plenty of copper ions in solution and we've got plenty of copper that can dissolve, and we just think about the one electrode, so we have to use a reference electrode for this. We will get some kind of steepness of curve near the 0 voltage. So if we have 0 volts, meaning we just put the electrode in and let it go to the voltage that it wants to go to, obviously the net current is 0 because no current can pass. So if we then force it to that voltage with an external power supply, we will still get 0 current. It's unsurprising. If we make it negative compared to that, we'll get negative current, and if we make it positive compared to that, we'll get positive current. And there's no logical reason why the 0 should be why it should be different below and above the 0 line for this particular example. In this particular example, we've got copper in solution already, and we've got copper as our electrode. We've got a bare copper surface, and we have a dynamic equilibrium at 0, so it's going in both directions, so we can just push it a little bit in one direction and a little bit in the other direction. As we increase the voltage, we will get more and more current, but it won't continue for very long, because eventually we will have the problem that we will not be able to get the copper ions away from our electrode. Or in this direction, it's also going to stop at some point, because we will use up the copper ions that are close to our electrode, and then there will be none. So if I draw that, we've got our surface here. This is our metal surface, and close to the electrode, we've got a little bit of special solution that is at either 0 concentration, when we've reached an extreme, or it's at very high concentration and we can't get any more in. It's at the Nernst concentration, so we can't get any more in if we're going upwards. And then at that point, we would expect it to be very difficult to get more current if we increase the voltage. So we will see the current will curve off. It's not necessarily symmetrical, because this effect here on this direction, we're using up the ions that are already in solution, and we've got 0 here. It turns out, weirdly, so this is possibly a difficult concept. I know this is sometimes a difficult concept. It turns out that once we've got the concentration down to 0, in close to the electrode, it doesn't matter what voltage we put on. We cannot get more ions to come further, faster. So we've got copper 2+ here. Sorry, it's a bit hard to write this way around. Copper 2+ here. They're diffusing in. And you would think, if we make this electrode more negative, you would think we would be able to pull them in harder. It looks like it goes back up, but that's just because everything's wonky here. If we imagine that's the case, then we would expect this to go at a different angle afterwards. So we would expect this to curve off, but never to go to 0. It would carry on getting more and more. And it does to a certain extent, but not nearly as much as we would expect, because we make our electrode negative. There are other ions in here that are positive. So in this case, it would be positive hydrogen ions, for example, depending on what the solution is. Or we just push away the sulfate ions, making this area relatively positive. Relatively positive. And so the copper ion out here doesn't see the electrode as being negative. If we push negative ions out into here, then the area close to the electrode will look like it's not charged there. If we're inside that region, we're not actually being pushed with the voltage further in. What that means is that it's very hard to increase the current beyond whatever the concentration can support. We can stir it. That will make the copper ions move closer. So stirring does improve it. But there's always a layer close to our surface which isn't moving, and that will still have no copper ions in it. On the other direction, it will become saturated with copper ions, and we get into danger of precipitating something like copper hydroxide, copper oxide or something onto our electrode if we're not careful. And that usually means practically that our current also saturates at some value, and it's hard to get it to go up past that. So that's what our curve will look like. The shape of this is not exactly straight. It has it's actually curved, but that's the general form that we would expect. If we have another process that can go on, so let us go on the reduction side maybe. So we're making copper, and then we can make maybe zinc further along. Or let's make zinc. So we've got copper 2+ depositing, and then we have zinc 2+ depositing on top, or at the same time, because this one doesn't stop. So we've got zinc 2+ also depositing at a higher negative voltage. This is what we're controlling. The x-axis is typically what you control. I, the current, is what you measure. If we go this direction, we are dissolving it. So we're stealing electrons from the solution, we're discharging copper ions, but eventually we'll start to discharge water, and we will get, so we're removing electrons from it, so we will be, what are we doing? Yes, we're removing electrons from it, so we'll be making protons from water, and so our current will also go up. If we are breaking the electrolyte in that case, there is comparatively more of it. So the current, the potential amount of current that we can draw is way higher than the potential amount of current that we can draw from any other process, because just there's a lot of electrolyte there. We're still limited by the electrode area, and in this case, if we're making bubbles at the surface, we will have weird things go on because we will be blocking parts of the area with the gas bubbles. So as a last part for today, we will consider just the positive part where we're dissolving copper. So we've got our piece of copper. As we make it more and more positive, it dissolves faster and faster, and then we get to a point where we can't get more copper into the solution close to the electrode, and so it has to diffuse away. If we think about what would happen if we increase the voltage faster, so if we, instead of changing voltage and waiting for a long time to see what current we get, we change the voltage over time, then we can get ahead effectively. If we get to here, for example, we would be dissolving copper as fast as it can into the solution. But if we get there quickly, then we will get there before there's much copper already there. At this point, if we go infinitely slowly, effectively, we've got copper in solution already, and so we can't get it to diffuse away, so it's just diffusing at the speed it's diffusing away. But if we get there quicker, there's not any in there, so we've got more space for it to go into. So we would expect to see a current similar to this, but it will go up past, and then it will come down to this value. It goes past because there is no copper in solution close by. If we go fast enough, there's none at all. If we go at an intermediate speed, there's some in there, and so our current capacity is higher, but only for a certain amount of time. So if we stop there, it would go down to this value. This is the sort of infinite value, the infinite time value. But if we get there very fast, we can have a lot more current. But if we go past too fast, or if we go too far past, it will eventually saturate, and it will be coming back down to this value. The lines are the same if we go far enough. If we sweep it faster, we will get the same, but higher. So we'll be able to do the same thing. We overshoot the voltage slightly more. This tells us that we're in this interesting room, this interesting space where we're between thermodynamics and kinetics, where we've got kinetic effects and thermodynamic effects causing us to see things at the same time. That's complicated enough for today, so we will stop there. So if we change our voltage very quickly, we can get temporarily more current, but it will eventually fall back down to the same value. If we change our voltage very slowly, then all we see is the diffusion current which is a constant value. If we come back, now that we've done that, then we've got more copper in solution, and so our 0 will have shifted, and so we will now, on the way back, tend to have a negative peak or have a shift in our curve because we've got copper dissolved and it's close to our electrode still. If we're going up and down, so this one is infinitely slowly, so it will come back, assuming we've got an infinitely large container of liquid. There, if we come back infinitely slowly, it will look exactly the same. But if we go to a real system where we're sweeping up and down, when we sweep back, we will have some copper in solution already. And so our voltage will be lower. Our current will be lower at the same voltage. And as we get down to where it was 0, we'll actually get negative current because we've got more copper in solution after the first cycle. If we carry on sweeping up and down, we will eventually get to a steady state, but there will be a gap between these two, which is how much copper do we make up here and how much copper do we use up at the bottom end. That will determine how much space there is between these two lines, which are effectively the upsweep and the downsweep. So that will do for today. We will come on to what happens with oxide layers next time maybe.